Dr. D here, and today we're going to learn about the equilibrium constant, how we can calculate it, figure out what does and doesn't affect it, and various ways we can manipulate this very important constant. So let's dive into it in Content with Content. So when talking about equilibrium, we need to first take a step back and talk a little bit about kinetics, or the speed a reaction takes place. So for example, we're going to look at nitrogen tetraoxide as it forms nitrogen dioxide. So we can take a look at the concentration versus time for this reaction, and we can also take a look at the rate of the reactions compared to time. So as the rate of our N2O4 turns into NO2 is going to slowly be decreasing as our concentration of our N2O4 is also decreasing. And then the rate in which the NO2 converts into N2O4 is going to increase as the rate of the NO2, or as the concentration of NO2 is increasing. And at some point, we'll see that the rate of our forward reaction, the N2O4 converting into NO2, equals that of our NO2 forming N2O4, the reverse reaction. And at that point, they're going to be producing at the same rate, and then our equilibriums are going to flatten out and are going to remain constant. So that's how this equilibrium thing is going to work. So our concentrations are going to remain constant once we reach equilibrium. So we can look at this a little bit mathematically and figure out how much of a particular reactant or product we're going to have with these equilibrium constants. So we're going to look at the generalized reaction where we have A with a coefficient of lowercase a plus B with a coefficient of lowercase b yields C plus a coefficient of lowercase c plus D plus a coefficient of lowercase d. And we can say that our equilibrium constant, K, is equal to the concentration of products over the concentration of reactants. And so the way this looks mathematically is that we're going to have our concentration of C raised to the coefficient of C times the concentration of D raised to the coefficient of D divided by the concentration of A raised to the coefficient of A and concentration of B raised to the coefficient of B. And I want to talk a little bit about some of the rules involved with our equilibrium constant. First thing is that our equilibrium constant is a function of temperature. So at different temperatures, that's going to change the value of the equilibrium constant. Now there's a few things that don't change our equilibrium constant, and that would be the initial concentrations, the volume of the container, and any addition of catalyst. Now, one of the things is if we have a very large equilibrium constant, normally it's something on the factor of 10 to the 10. This means that, or often we would refer to this reaction going to completion, or we say the reaction goes to completion. And this means that the equilibrium will favor products. An example of this is HCl plus water, forming hydronium ion and chlorine ions. And this has an equilibrium constant of 10 to the 7. So we say this one goes to completion. Another one is if we have a small value for our equilibrium constant, this means that the reactants are going to be favored once equilibrium is achieved. Example of this is nitrogen gas plus oxygen gas forming 2-nitric oxide. And this equilibrium constant is 10 to the minus 25. So basically, if you have anything around 10 to the minus 10, this is a very small K. And in this case, this is actually a really good thing because we won't be able to breathe on planet Earth otherwise. All right, so a couple other things to note about K is that depending on how you write the reaction, it's going to have its own value for the equilibrium constant. So it's very important, and we'll get through this a lot when we're talking about how to manipulate the equilibrium constant. But just keep in mind, how you write the reaction is insanely important for the value of K. The products are in the numerator, and the reactants are in the denominator. The reactants are anything that's on the left side of the yield sign, and the products are anything that's on the right side of the yield sign. And one thing to note is that the equilibrium constant only works for when we're actually at equilibrium. So it only works for equilibrium concentrations once equilibrium has been achieved. And the equilibrium constant of a reverse reaction is going to be equal to the inverse, or 1 over, the forward reaction. So for instance, let's say our forward reaction was A yields B, then our equilibrium constant would be concentration of B over concentration of A, products over reactants. And if we want to flip that around, and now we have B yielding A, then the equilibrium constant of this reverse reaction would be concentration of A over concentration of B, which again is 1 over our value for the equilibrium constant of the forward reaction, or the inverse of it. And then lastly, and this one's kind of important, is pure solids and liquids are not included in your calculation for the equilibrium constant. They're already factored in. The reason for this is when we talk about concentrations, this is for like solutions and things, this is moles per liter. So we figure out how many moles we have in a given area. If we're talking about gases, we talk about partial pressures, and this is letting us know how many moles of a particular gas we have in a certain area. But when we have pure solids, well, we know what their densities are. If we have pure liquids, we also know what their densities are at a given temperature. And so you don't need to go back and recalculate this. It is already factored into the equilibrium constant value because the densities are not going to change for those pure solids and pure liquids. All right, so let's go ahead and look at an example. Let's say we have nitrogen gas plus 3 hydrogen gas molecules yields 2 ammonias. And so let's say initially we have only 1 molar of our ammonia, and we do an experiment, we measure out what it is at equilibrium, and we find that we have 0.399 molar N2, 1.197 molar H2, and 0.203 molar NH3. And so if we want to calculate the equilibrium constant, we'd say that our equilibrium constant is going to be equal to our concentration of NH3 squared divided by our concentration of N2 divided by our concentration of H2 cubed. And then we can plug in the values for our equilibrium concentrations. So we have 0.203 squared divided by 0.399 divided by 1.197 cubed. And if we plug all that in the calculator, we'll get out 0.0602 for our value of K, or our value of our equilibrium constant. And so that would be one experiment we could do. But let's say we want to do another experiment, and this time we want to use a different amount of initial concentrations. So we initially start with 2 molar N2, 1 molar H2, and 3 molar NH3. And after weight, let everything achieve equilibrium, we find that our concentrations would be 2.59, 2.77, and 1.82 molar, respectively. So now we can solve for K again. It's going to be the exact same way we did earlier. We're going to have our equilibrium concentration. So we have NH3 squared divided by N2 divided by H2 cubed. We'll plug in those values and we'll have 1.82 squared divided by 2.59 divided by 2.77 cubed. And that will give us a value of 0.0602. Now, one thing you may notice is that both these values are the same. And it makes sense to some degree because this is an equilibrium constant. It is in fact a true constant. So no matter what value we have of our initial products and reactants, if we reach equilibrium, the equilibrium constant will always be the same if we stay at the same temperature. So that's how we can calculate K. And normally when we talk about K, as I've done at the beginning of this video, we really mean Kc. Kc is the equilibrium constant based on concentration. There's another term, Kp, which is the equilibrium constant based on partial pressures. So let's take a look at an example where the generalized equation of A plus B gives C plus D again, but this time they're all gases. Well, if this is the case, we want to calculate our Kp. This is our equilibrium constant based off of pressure. It's going to be our partial pressure of C raised to its coefficient times the partial pressure of D raised to its coefficient divided by the partial pressure of A raised to its coefficient divided by the partial pressure of B raised to its coefficient. So a very similar thing, it's just now we're dealing with partial pressures, so typically atmospheres. And so if we look at 2NO plus chlorine gas, that's going to give us 2 nitrosyl chloride, or NOCl. And we can determine Kc the same way we were doing earlier, or we'll have NOCl squared divided by NO squared divided by Cl2. And then we can also do it for Kp, our equilibrium constant based on partial pressure. So it's going to be the partial pressure of NOCl squared divided by the partial pressure of NO squared divided by the partial pressure of Cl2. So very, very similar, and we can actually relate these two values to each other. So normally if you're working with molarity, use Kc. If you're working with atmospheres, use Kp. But sometimes you're going to have a mixture of the two. So to get into this relationship between Kp and Kc, I want to talk about the ideal gas equation. So this is where we have pressure of a gas times the volume of a gas is equal to the number of moles of a gas times the ideal gas constant times the temperature. So PV equals nRT. And we can rearrange this a little bit to solve for our moles of gas or to isolate it. And we'll have N is equal to PV over RT. So keep this in mind as we go to our kind of quasi-example here. So we can have our concentration of NOCl, and again, remember, concentration is just moles over liters. So it's our number of moles of NOCl divided by a certain volume. And we have our ideal gas equation where we solve for moles, and our number of moles is the pressure times the volume divided by the ideal gas constant divided by temperature. So PV over RT. So we can plug that in for our moles, and we'll get the partial pressure of NOCl times the volume divided by the volume, and then divided by RT, or the ideal gas constant and temperature. So now we can, since we have volume over volume, we can actually reduce this down a little bit. So it will just become the partial pressure divided by RT. And so whenever we have a concentration, we can just plug in the partial pressure divided by RT, and we'll plug this into an example here of our 2NO plus Cl2 yielding 2 NOCl. So for Kc, we already know this is going to be NOCl squared divided by the concentration of NO squared divided by the concentration of Cl2. But now we can replace those concentrations with partial pressures divided by RT. So I have partial pressure of NOCl divided by RT squared, partial pressure of NO divided by RT squared, and partial pressure of Cl2 divided by RT. Now we can go ahead and factor out 1 over RT out of each of these. So we'll end up with 1 divided by RT squared times the partial pressure of NOCl2, or NOCl squared, divided by 1 over RT squared times the partial pressure of NO2 or NO squared, and divided by 1 over RT divided by the partial pressure of Cl2. All right, then we can group everything and factor them into essentially one side, so we'll end up with 1 over RT squared divided by 1 over RT cubed. We'll later reduce this down to simply be divided by 1 over RT. And then we have partial pressure of NOCl squared divided by the partial pressure of NO squared divided by partial pressure of Cl2, which is the exact same thing we had for Kp. So we'll just substitute that in for Kp. So we'll end up with Kp over 1 over RT is equal to Kc. Now, we can go ahead and isolate Kp and multiply both sides by 1 over RT. So we'll get Kp is equal to Kc divided by RT in this case. So to generalize this a little bit for the actual equation or relationship between Kp and Kc, we can say that Kp, the equilibrium constant of, according to partial pressure, is equal to RT raised to delta N, which is our change in moles of gas, times Kc. So for our change in moles of gas, we can see that we have two NO gas molecules plus Cl2 gas molecules, so a total of 3 moles of gas in our reactant side. And we have 2 moles of our nitrosyl chloride, or 2 moles of NOCl, on our product side. So we have 3 moles of gas going to 2 moles of gas. So for our change is always going to be final minus initial. So we're going to have 2 moles of gas minus 3 moles of gas. Again, final minus initial, so 2 minus 3. That's going to give us a -1. And so in this case, we'd have RT raised to the -1 times Kc. So raising it to -1 just means 1 over RT, which is what we got. Okay. So besides going from Kp to Kc, there's several other ways we can manipulate our equilibrium constant. One of those ways is to use a multi-step reaction. So for multi-step reactions, this is where you are making a particular product and that becomes a reactant in a following reaction. So let's say we have A going to B, that have an equilibrium constant of K1, where we have concentration of B divided by concentration of A. And then B can convert to C, so we have B yielding C, and that would give us K2 is concentration of C divided by concentration of B. So if we want to look at the overall reaction, we could say we add up all of our reactants. So we'll add up everything on the left side of both reactions, so A plus B, yields everything on the product side. So we'll add up all of our products together for both reactions, so B plus C, and that gives our K overall, or K3 in this case, of concentration of B times concentration of C divided by concentration of A divided by concentration of B. Or we could figure out numerically by just multiplying K1 times K2. All right, so if you're adding your reactions together, you're going to multiply them together for your equilibrium constants. Now we can reduce this down a little bit so we don't even have to worry about B anymore, because you'll see that as we're forming B, we're also consuming B. And we end up with concentration of B over concentration of B, which is just 1. So we can factor all that out, and we'll end up with A going to C, because as B is being produced, it's also being consumed. Will give us K3, our overall reaction, of concentration of C over concentration of A. So we can factor out B altogether. All right, another way we can manipulate K is through multiplication. So again, how you write your reaction is very important. So we have A going to B. We ended up with the same thing where we have K1 is concentration of B over concentration of A. But now if we write it as 3A yields 3B, so we just multiply the reaction by 3. Now we're going to get K2 being concentration of B cubed divided by concentration of A cubed. And so what this is going to do is we can essentially say it's similar to the first one of K1, but cubed. So whatever you multiply by, when you're finding out the equilibrium constant, you want to raise it to that same exponent. So since we multiply by 3, we want to raise it to the exponent of 3. And we already touched up on how you can do reverse reactions, but I want to explain a little bit more explicitly. So for a reverse reaction, this is when you essentially flip your reaction. So we have A plus B yielding C, giving us K1, where our concentration of C divided by our concentration of A divided by our concentration of B. And if we write the reaction in reverse way, where we have C yielding A plus B, then this will give us K2 being concentration of A times concentration of B divided by concentration of C. Or another way of thinking of this is it's going to be our K1 raised to the negative 1, or the inverse of K1. So simply just 1 over K1 will give us the same result. All right. And the last way we can manipulate K is through changing the temperature. So K, our equilibrium constant, is a factor based on temperature. But you can actually do this in a known way. It will change in a quantifiable way. And so this is done through the Van 't Hoff equation, which seems a little daunting, but it's not too bad. We have the natural log of K2, our new equilibrium constant, divided by K1, our previous equilibrium constant, is equal to the negative, and try to keep in mind that negative needs to be there. The negative of our enthalpy of our reaction divided by R, the ideal gas constant, multiplied by 1 over T2, which is our new temperature, minus 1 over T1, our previous temperature. And so we can actually switch from one equilibrium constant to another, provided we know the standard enthalpy of the reaction, and we can figure out what the equilibrium constant should be at our new temperature. All right, so we went through and did a lot of things to manipulate K. One last thing. We must always keep in mind to leave our temperatures in Kelvin. Sometimes you can do chemistry and it doesn't really matter if it's in degrees Celsius or Kelvin, normalized for change in temperature. But for this one, you definitely want to make sure you have it in Kelvin, otherwise it will give you a wrong result. All right, so we figured out several ways to manipulate K, but what happens if we're not actually at equilibrium? Well, that's where this reaction quotient will come in, or Q will come in. All right, so it doesn't have to necessarily be at equilibrium, but it's going to follow a very, very similar process. So we look at our generalized reaction of A plus B yielding C plus D. We can find that Q is going to be pretty much the exact same thing K was, where we have products over reactants. So concentration of C raised to C, concentration of D raised to D, divided by concentration of A raised to its coefficient, concentration of B raised to its coefficient. So it's the exact same process. It just doesn't have to be at equilibrium. Now what we can do with this is now we can compare it with our equilibrium constant and figure out which way the reaction is going to go. So if our equilibrium constant is equal to Q, then that means our reaction is already at equilibrium and there's not going to be any net change. The concentrations are going to remain constant. If our equilibrium constant is greater than Q, our reaction quotient, then that means the reaction is going to shift to the right. It's going to shift from reactants to products, and we're going to be making more products as we approach equilibrium. If our equilibrium constant is less than Q, then our reaction is going to shift from right to left, or from products to reactants. And as we approach equilibrium, we're going to be making more reactants. So as long as you always write this as K then Q, so do it alphabetically, one trick you can kind of use is whichever way the kind of sign is pointing. It kind of looks like an arrow. that is the direction you'll be shifting the reaction. All right, so if K is greater than C, it's going to shift to the right. If K is less than Q, it's going to shift to the left. All right, well, so this is all I have for you. Talking about the equilibrium constant, we talked about several ways that you can calculate it, how you can manipulate it, how you can convert from one to the other, and even a little bit on how you can do what you can figure out if you don't know, if you're not currently at equilibrium. But anyway, I hope you enjoyed this and learned something. And as always, keep thinking, and I'll see you next time. Goodbye.